Chapter 22. Restoring the digestive state. Restoring the digestive state requires re-establishing the conditions under which the system can operate in sequence. Digestion does not begin with food composition. It begins with permission. The nervous system determines whether the body allocates resources toward processing incoming material or diverts those resources elsewhere. When this state is constrained, acid production declines, enzyme release weakens, bowel flow becomes inconsistent, and motility loses coordination. The goal is not to force output at isolated points, but to restore the upstream conditions that allow the entire sequence to activate as a single system. The first layer of restoration occurs at the level of neural input. Sensory engagement with food initiates the cephalic phase, which prepares the stomach, pancreas, and biliary system before swallowing occurs. This phase is mechanical and predictable. When food is seen, smelled, and tasted under conditions of low stress, signals are sent that increase secretory output and coordinate downstream activity. When this phase is absent or reduced, the system begins in a weakened state. Restoring it means allowing sufficient time and attention for these signals to form before food enters the stomach. Pacing reshapes how these signals are maintained. Rapid intake compresses the digestive sequence, forcing multiple phases to overlap without proper transition. The stomach receives material before it is fully prepared, and downstream organs respond to incomplete signals. Slowing the rate of intake extends the time over which signals are generated and sustained. This allows acid production to reach effective levels, enzymes to be released in proportion to substrate load, and bowel flow to align with lipid arrival. The sequence regains structure because each step has the time required to activate and complete its role. Mechanical processing in the mouth contributes directly to restoration by reducing particle size and increasing surface area. This change is not only physical. It alters how the stomach perceives incoming material and how quickly it can act on it. Smaller, well-processed particles allow acid to interact more uniformly, supporting protein unfolding and preparing substrates for enzymatic cleavage. This reduces the burden on downstream processes and improves the efficiency of the entire sequence. Gastric conditions must be allowed to develop fully. Acid production is not instantaneous. It increases in response to incoming signals and substrate presence. When intake is rushed or when prior phases are weak, acid levels may not reach the threshold required to properly modify food structure. Allowing sufficient time between intake and progression to the next phase ensures that proteins are unfolded and that the material entering the small intestine is in a state that can be further processed. Coordination between the stomach and small intestine defines whether the sequence continues or breaks down. The release of gastric contents must match the capacity of the intestine to process them. When this coordination is restored, substrates enter in controlled amounts that can be matched by enzyme release and bile flow. When it is not, the intestine receives material that exceeds its processing capacity, leading to incomplete digestion and downstream effects. Restoration focuses on re-establishing this balance so that delivery and processing remain aligned. Lipid digestion plays a central role in stabilizing the restored state because it provides a sustained input that extends beyond the rapid phases of carbohydrate processing. When fats are properly emulsified and absorbed, they create a prolonged delivery of substrates that supports steady energy production and consistent signaling. This stabilizes the system and reduces variability in downstream responses. Ensuring that bile flow and emulsification occur in coordination with lipid intake is therefore a key part of restoring overall function. Restoring the digestive state is not achieved by targeting individual symptoms or isolated steps. It requires rebuilding the sequence from the beginning so that each phase prepares the next. Neural input initiates the process. Mechanical and chemical preparation in the stomach establishes substrate structure, coordinated release aligns with intestinal capacity, and transport systems deliver nutrients in a controlled pattern. When these elements are reconnected, the system returns to a state where digestion proceeds as an integrated function rather than a series of disconnected events. Nervous system regulation. Nervous system regulation defines whether digestion is allowed to operate as a coordinated sequence or remains constrained at every level. The digestive system does not function independently. It is governed by neural inputs that determine blood flow, secretion, motility, and timing before any chemical processing begins. When these inputs are aligned, the system transitions into a state where resources are directed toward digestion. When they are not, output is reduced regardless of food composition or nutrient density. Regulation at this level sets the ceiling for everything that follows. The transition into a digestive state begins with parasympathetic activation, which increases secretory output and organizes motility into patterns that support mixing and controlled progression. Gastric acid production rises, pancreatic enzymes are released in proportion to incoming substrates, and bile flow aligns with lipid presence. These responses are coordinated through neural signaling that integrates sensory input with internal conditions. When this activation is incomplete, each of these outputs is reduced. The stomach produces less acid, the pancreas releases fewer enzymes, and bile delivery becomes inconsistent. The sequence weakens before it has fully begun. Sympathetic activation produces the opposite effect by reallocating resources away from digestion. Blood flow to the gastrointestinal tract decreases, limiting both secretion and absorption. Motility patterns shift, often becoming irregular or accelerated in ways that reduce contact time between substrates and enzymes. This changes how material is processed and where it accumulates within the system. The reduction in perfusion also affects the epithelial surface, decreasing the efficiency of transport systems that move nutrients into circulation. These changes occur together, creating a state where the digestive system operates under constraint. Regulation is not binary. It exists along a range, and the digestive system responds proportionally to the degree of activation. Partial activation produces partial output. This creates a condition where digestion may appear functional but operates below capacity. Substrates are processed incompletely, signals are weakened, and downstream effects begin to accumulate. The system adapts to this reduced state, but the adaptation reflects limitation rather than restoration. Neuroregulation also determines how signals propagate through the sequence. Early phase signaling from sensory input influences gastric activity, which in turn shapes pancreatic and biliary responses. When the initial signals are weak, the downstream responses are proportionally reduced. This propagation effect means that small changes in neural input at the beginning of the sequence can produce larger changes in output later on. Restoring regulation at the top of the sequence, therefore, has amplified effects throughout the system. Lipid digestion depends heavily on this regulation because bile release and coordinated motility are required to process fats effectively. When neural input supports proper timing and flow, lipids are emulsified and absorbed in a pattern that stabilizes energy delivery and signaling. When regulation is impaired, this coordination breaks down, reducing lipid processing and removing a stabilizing influence on the system. Nervous system regulation therefore acts as the primary control layer for digestion. It determines whether the system operates with full capacity, partial output, or suppression. Restoring this regulation aligns blood flow, secretion, motility, and timing, allowing the digestive sequence to function as an integrated process. When this control layer is stable, the downstream processes it governs regain their structure and efficiency. Re-establishing parasympathetic dominance. Re-establishing parasympathetic dominance means restoring the internal conditions under which digestion is permitted to run as a full sequence rather than a constrained process. The parasympathetic state is not an abstract relaxation response. It is a specific physiological configuration where blood flow is directed toward the gastrointestinal tract, secretory activity increases, and motility organizes into patterns that support mixing, breakdown, and controlled progression. When this state is absent or only partially activated, digestion proceeds with reduced output at every level. The goal is to shift the system back into a state where these processes can occur without restriction. The transition begins with sensory engagement and pacing. The cephalic phase depends on visual, olfactory, and gustatory input to initiate digestive signaling before food enters the stomach. When meals are approached without interruption and with sufficient attention, these signals activate neural pathways that increase gastric acid production and prepare downstream organs. This is a mechanical process. The presence of food cues under low-stress conditions generates predictable changes in output. When this phase is compressed or bypassed, the system starts in a weakened state and must attempt to catch up after food has already entered the stomach. Breathing patterns directly influence this transition by altering autonomic balance. Slower, controlled breathing increases parasympathetic input and reduces competing signals that suppress digestive activity. This change affects heart rate, vascular tone, and neural signaling to the gastrointestinal tract. As parasympathetic influence increases, blood flow to digestive organs rises, supporting secretion and absorption. The effect is not isolated to one organ. It shifts the entire system toward a configuration that favors processing incoming material. Posture and physical positioning contribute to how this state is maintained. An upright and stable position supports coordinated motility and reduces mechanical constraints on the stomach and intestines. When the body is compressed or moving rapidly, signals that support digestion are reduced and motility patterns become less organized. Maintaining a stable position during intake allows neural signaling to remain consistent and supports the mechanical aspects of digestion. Consistency reinforces this state over time. The nervous system adapts to repeated patterns of input. When meals are consistently approached under conditions that favor parasympathetic activation, the system begins to anticipate and prepare for digestion more effectively. Secretory responses become more proportional, motility patterns stabilize, and coordination between organs improves. This adaptation reflects repeated exposure to conditions that allow the sequence to run as designed. Lipid digestion highlights the importance of sustained parasympathetic activity because bile release and emulsification depend on coordinated signaling over time. When this state is maintained, fats are processed efficiently and provide a prolonged supply of substrates that support stable energy production. When it is not, bile flow becomes inconsistent and lipid processing is reduced, removing a key stabilizing input to the system. Re-establishing parasympathetic dominance therefore restores the foundational state required for digestion to operate as a coordinated system. It aligns neural input with the structural and functional demands of the digestive sequence, allowing each phase to activate in order and at sufficient capacity. When this state is consistent, the system regains its ability to process food effectively, and the downstream effects that depend on proper digestion begin to stabilize.